Welcome. So in this video, we are going to look at composite functions, the continuity of those composite functions, and the limits of composite functions, and see how continuity can help us evaluate those limits. There is a theorem in the book that says that if a function g is continuous at the value x equals a, and a function f is continuous at g of a, then the composite function f dot g will also be continuous at x equals a. So that means that the limit as we approach a of f of g of x is the same thing as the function value at a. So that's f of g of a. Said otherwise, this theorem implies that if I compose continuous functions together, I also get a continuous function. It also implies that if I have two functions f and g that are continuous on their domain, then the resulting composite function f dot g will also be continuous on its domain. That's the case for most functions that we know. Most functions that we know are functions that are continuous on their domain. For example, polynomial functions, root functions, trig functions, logarithmic functions. Okay. Finding where those functions are continuous is the same as finding their domain. Now, what the theorem says is that if I compose those types of functions, I will also get functions that are continuous on their domain. And if you look back again at the conclusion of the theorem, it's basically just a direct substitution rule. So evaluating the limit at a is the same thing as evaluating the function at a. As an example, if we look at the limit as we approach one of the natural logarithm of x squared plus 1 over 2x, evaluating this limit will be easy if 1 is part of the domain of the function. That is, if it's part of the values that make this function continuous. Let's see if there is a problem if we replace x by 1. Well, if we look at the inner function x squared plus 1 over 2x, is it defined at 1? It wouldn't be if we would be dividing by 0 by replacing x by 1, but it's not in this case because 1 is not equal to 0, which is the only value that makes the denominator equal to 0. Now, the lateral logarithm is only defined for positive values. So if we replace x by 1, we get 1 squared plus 1 over 2 times 1. That simplifies to 1, and that's actually a number that is positive. So there isn't any problem here replacing x by 1 overall, and by replacing x by 1, we will get the value of this limit. As a side note, if we're interested in finding where the composite function is continuous, as said before, it's equivalent to finding its domain. So what would be the domain here? Would be all values of x where the rational function is positive, so that the natural logarithm is defined, and where the rational function is defined as well. So all values where the denominator isn't equal to 0. So in that case, that's just x not equal to 0. So I have two conditions that have to be satisfied. If I look at the first one, saying that x squared plus 1 over 2x is a strictly positive number, that means that the numerator and the denominator must have the same sign. Either they're both positive or both negative. But if we look at the numerator, x squared plus 1, no matter what x is, it's always going to be positive. So the ratio will be positive if the denominator is positive as well. So when 2x is positive, in other words, when x is positive and not equal to 0 because of the second condition. So overall, that means that the domain is all values of x where x is strictly greater than 0. And the domain in that case is where the function is continuous. So finally, the limit we had previously, we can use direct substitution to evaluate it. And that's just ln of 1, there's a typo, it's 1 squared plus 1 over 2 times 1, and that simplifies to ln of 1. I could leave my answer like this, but I might not get full marks because I can simplify this natural logarithm. This natural logarithm of 1, what's a natural logarithm again? It's the inverse function of the exponential function. So we're looking for an exponent. So a natural logarithm is an exponent. It's the exponent to which we raise e in order to get 1. So what value is that? Well, it's 0. Because e to the 0 gives me 1, and that's our final answer. Thank you for watching.